So, Louis de Broglie, my husband and I had an argument about how you pronounce that last night, so I'm going to avoid saying it now. He proposed in 1924 that particles could have wave-like character in addition to their particle character. So we see this most clearly when we look at electron diffraction. So the interference pattern that we see in electron diffraction is not caused by pairs of electrons interfering with each other, one electron interfering with another, but by single electrons interfering with themselves. Is that disturbing? Should be. So what are we talking about here? So this is a double slit experiment, but with electrons instead of light. Remember the guy with the box in the YouTube video? Right? So this is a similar idea, but instead of light, we're sending electrons through a double slit. So you send electrons through this double slit, and we get an interference pattern over here, very similar to what we saw with light. Light is a wave. This demonstrates that electrons also behave like waves. Now, of course, you can't see the electrons here. They don't make a physical light on the screen, but you use a detector and you can reproduce a similar idea. So that's what the electrons do. If electrons were particles, then we would expect to see two bright lines. Think of throwing baseballs through a doorway, right? Either the baseball hits the wall and it doesn't go through, or it hits the doorway, goes through the doorway, hitting nothing, and just keeps traveling in a straight line and hits over here. That's predictable. That's something we understand. But what actually happens with these electrons, which are particles, they form an interference pattern. So this demonstrates that they are also behaving like waves. So the wave nature of the electron is an inherent property of that individual electron. And de Broglie predicted that the wavelength of a particle was inversely proportional to its velocity. So electrons are not electromagnetic radiation. How fast does electromagnetic radiation travel? The speed of light, right? Because it's light, it travels at the speed of light. Electrons are not light, so they travel at speeds other than the speed of light. But there's a relationship between the velocity and the wavelength. The wavelength is equal to Planck's constant divided by the mass of the electron times its velocity. Now, that looks an awful lot like nu, but that is v for velocity. Very confusing. And here's Planck's constant again. You don't need to memorize that. I'll give that to you. So we can predict or calculate the wavelength of the electrons from their velocity or vice versa. So let's do that, right? So what's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. Okay, so we're being told that the wavelength is 1.2 times 10 to the minus, oh my goodness, 10 to the minus 10 meters. And we're asked to find the velocity. Well, we've got that de Broglie relation. So the wavelength is equal to Planck's constant divided by the mass times the velocity. We could rearrange that equation. I'm not going to do that, but velocity equals h over m lambda. Just rearranging the equation, solving for velocity. So we need h, which is Planck's constant. So that was given in the previous slide, 6.626 times 10 to the minus 34. Funny units, joules times seconds, We'll just go along with it. We've got the wavelength here in meters, and then we need the mass of an electron. Hey Siri, what's the mass of an electron in kilograms?
Checking. The answer is 9.11 times 10 to the negative 31st power kilograms.
Thank you. You need to be polite to Siri. Yeah. 9.11 times 10 to the minus 31 kilograms. That's also a number you don't have to memorize. I can't quite remember it myself. That's the mass of an electron. So we've got Planck's constant, we've got the mass of an electron, we've got the wavelength. We can put these numbers in. So 6.626 times 10 to the minus 34 joule seconds divided by 9.11. I should be able to remember the first part of that. It's 911 times 10 to the minus 31 kilograms, and the wavelength 1.2 times 10 to the minus 10 meters. Now we can do the math. Oh, did I bring my calculator? I did. Awesome. 6.626 EE minus 34 divided by 9.11 EE minus 31 divided by 1.2 EE minus 10. Get a really big number here. So 6.06 times 10 to the 6. Now the units. You need to pay attention to the units. Some of you lost some points on the last exam because you needed to convert some units and you didn't. You just stuck the numbers in there and did the math. And it comes out not quite right. And not quite right is wrong, isn't it? It is. So let's look at what's going on with the units here. So we've got joules times seconds divided by kilograms times meters. That's a mess, right? We have to remember that a joule is a kilogram meter squared per second squared. Yeah, that's right. So a joule is a kilogram meters squared per second squared. And that's times seconds divided by kilograms times meters. So this second cancels one of the seconds, and the meter cancels one of the meters, and the kilogram cancels the kilogram, and the units end up to be meters per second. So the units here, meters per second, which is good because that's a unit of velocity. So it was important there that we use the mass of the electron in kilograms, because kilogram is the base unit in the SI system, and so that's the unit that's hiding inside the unit joule. So, any questions? Those electrons are moving really fast, but they're not moving at the speed of light. What if we ended up with a velocity that was 6.06 times 10 to the 10th meters per second? Would that be reasonable? No. Why not? Faster than the speed of light. Can anything go faster than the speed of light? Not really. Maybe, but things get really weird when that happens. So that's not going to happen in any of our problems. So the uncertainty principle. So electrons, I think of them as squirrely little rascals. They're difficult to understand. When you try to observe the wave nature of the electron, you can't observe its particle nature. If you observe its particle nature, you can't observe its wave nature. You can't see both at the same time. We observe its wave nature as the interference pattern in that double slit experiment. We observe its particle nature if we observe which slit the electron is passing through. And we can do that by shining a laser on there, and we can see which slit the electron's going through. But when we do that, it's kind of the two universe thing with the Schrodinger's cat. We force it to be one or the other. So an electron can simultaneously exist as a particle and a wave, but when we observe it, it has to be one or the other. So we say that the wave and particle nature of the electron are complementary properties. The more you know about one, the less you know about the other. So if we take this double slit experiment with the electrons and shine a laser beam across so that we can see which slit the electron's going through, we force it to act like a particle, and then we see two bright lines instead of the interference pattern. You turn off the laser so that you can't tell which slit it's going through, and you get the interference pattern back. It seems like the electron is sentient, that it is aware of what's going on. It isn't, but kind of makes you wonder sometimes. Is that disturbing? Should be disturbing. It bothers me. It's crazy. It's really, really crazy. And it's not just this experiment. Any experiment. You try to nail it down in one way, and you just get, less and less about the other. And Heisenberg actually quantified this. Heisenberg's uncertainty principle, we're not going to do a lot with this equation. But basically what this says is the more accurately you know the position of the electron, and to know its position, it would have to be a particle, then the less you know about its speed, and vice versa. So the uncertainty in its position, that's delta x, times the mass times the uncertainty of the velocity must be greater than or equal to Planck's constant divided by 4 pi. So we cannot simultaneously measure the position and the velocity of an electron. It's a bummer, but it is. So we have determinacy versus indeterminacy. Classical physics, particles move in a path that's determined by their present situation. Their velocity, their position, the forces acting on it determines where the particle will be. In quantum mechanics, we cannot know both the position and the velocity, and so we cannot predict the path that it will follow. This is called indeterminacy. We can only predict what's going to happen statistically. So we use statistics to develop a probability distribution map, and we can predict that, well, most of the time the electron is going to be in this region. Did I draw you a map of where Andrew was? No? I'll get to that in a minute. Remind me if I forget. So this is classical physics. Baseball player hits a ball. You can know its trajectory. You can know the velocity of the ball. You can know the force acting on the ball. You can predict where it's going to happen. You may not have thought about this, but being able to catch a ball, you are doing classical physics in your head. You are predicting where that ball is going to land. And when you watch a skilled athlete do this, it's pretty amazing. I've been watching high school volleyball. Oh my goodness. Those girls, somebody else sets the ball, and the ball's still way up by the ceiling, and they're up in the air, and the ball comes down at just the right time, and they slam it. It's amazing. That's physics that your brain does. And you're not even consciously thinking about it. But you can predict where that ball's going to be based on your experience. Electrons don't act like that. Baseball, you pitch the ball the same way, it goes the same place every time. If you pitch an electron, it doesn't go the same place every time. Spit them out exactly the same way, you would expect that they'd, go in the same area. No. One's here, one's there, one's over here. One might go up and hit this lady in the face. They could go all over the place. And so all we can do is give a probability. So there's a 20% chance that it's within this circle, a 40% within that circle, a 70% chance that it'll be within that circle. That's the best we can do. So this is where Andrew comes in. Andrew is my youngest child. Oh, he is such a youngest child. So this is a very rough sketch of my house. It's not a box, but close enough. And so if we were, and let's think of Andrew a few years ago when he was 2. So you think about, where's Andrew? Well, he's over there watching TV. Where's Andrew? Well, he moved around a little. He's still watching TV. Where's Andrew? He went to get a snack. Where's Andrew? He's in the bathroom. He's sleeping in my bed. I kicked him out. He's sleeping on the floor. He actually went and slept in his bed for a minute, bathroom, So there's these different places that Andrew can be. Maybe he's out in the front yard. He's playing in the backyard. Then there's the time he stole the neighbor's big wheel and rode it 3 blocks to his uncle's house, 2 years old. Right? So he's like over here. Right? So how can you say, where is Andrew? He's a lot like an electron. You can say, well, he's probably in the house. There's a bigger probability that he's at least on the property, but there's a chance that he's just nowhere to be found, somewhere completely unexpected. That's what electrons are like. And so we can't say, this is where the electron is. We can't have the Bohr model with its nice, tidy little orbits and say, here's the electron going in this nice little circle, and we can tell how fast it is and where it's going to go. Doesn't act like that. But we can say, here's a region of space that electron is probably in. Any questions or comments on that? How was that experience? Oh, yeah, that was fun. That involved getting in the car and driving in widening circles. And I live in Reedley, which is a small town, and so everybody knows I'm that crazy lady with too many children. And so a neighbor did spot him and say he went that way. And yeah, he was fine. He's still alive. He has 2 guardian angels, I'm convinced. That child.